Hello, welcome to lesson 4.09 chemistry, electron configuration and the periodic table. In this video, we're going to kind of wrap things up. We're going to bring things together. So we've been writing electron configurations for the first three periods. We've got period 1, 2, 3, 4, 5, 6, and 7. We're only going to go down this far. We're not going to worry about 6 and 7. But it's a little bit cumbersome, right? We've been using Aufbau diagrams and orbital diagram notations. Well, it turns out all you need is the periodic table. There's a beautiful symmetry here. So let's take, for example, let's go with neon. So I'm going to write neon in over here. Neon. And we've already done neon, and we know that neon is 1s2, 2s2, 2p6. So from previous lessons. You see, I'm going to hit focus real quick. It's a little blurry. Not too bad. Okay. Also, based on previous lessons, we know that neon is going to have 8 valence electrons. So we have 8 valence electrons because the second energy level is the highest occupied, and I have 6 in the P and 2 in the S. Well, if we look at neon's position, the first main energy level is going to correlate to the first row of the periodic table. And notice there's 2 boxes. That's because in the first main energy level, all we have is an s orbital. And so if I have hydrogen, I have 1s1. If I have helium, I have 1s2. Well, then we come down and we've got, remember, these are main groups. So just as a refresher. So main group is in blue. It's main group. And here we have our inner transition metals. These are non-main group. We'll do these in light blue. Non-main group. And these are our rare earth metals. They're also non-main group. So we have neon over here, and there's 2 boxes in the alkaline metals and the alkaline earth metals. Well, it turns out these 2 electrons will always fill an s orbital. And then, according to Aufbau, lowest energy fills first, then the 2p are going to fill. And notice there's 1, 2, 3, 4, 5, 6 boxes. And the periodic table, the cool thing is the periodic table was developed before scientists knew anything about electrons. We know that an element's, an element's placement initially, elements were placed by the number of protons. Actually, initially they were placed by their properties. They're placed by their properties. They didn't know anything about protons and electrons when they put this table together. And then when they discovered protons, they found out that the number of protons correlates to its position. Not only that, but electrons and electron fill correlates to the periodic table. So hopefully you can kind of appreciate how cool that is. That would be like drawing the treasure map with no idea where the treasure was, and then digging some years later and finding out there was actually treasure there. So in order to find an element's electron configuration, all we have to do is look at the periodic table. So let's take, for example, silicon, which is right here. Without even looking at an Aufbau diagram, I can use the periodic table to determine that silicon is going to be, so let's do silicon up here. The first row is going to be 1s2. Then I go to 2s2. And then I go to 2p, and those are all full, 2p6. And then I go to 3s2. And then I go to 3p2. So that means that the electrons for silicon are going to fill in this order. What about, let's do this guy down here. Let's do titanium. Titanium. So I'm going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, this is where that fill order exception takes place. Instead of going to 4D, we have the 3Ds first. And you have to memorize this. So what you want to do is you want to remember that you go from 4S to 3D. So I have 3D2. In the book, it's going to have it as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, 4s2. So it'll flip, and you have two valence electrons. These don't count as valence electrons. 4 is the highest main energy level. Well, when we start to get down into the 6s and 7s, these things get super long, and it's a little bit annoying. And so we go into something called noble gas notation. It's a shortcut for the shortcut. Noble gas notation. And what we do is, instead of writing out, so if I was doing titanium, instead of writing out the 1s2, 2s2, 3s2, 3p6, what I would do is I would put noble gas for the row before, which is argon, and then add 4s2, 3d10. So let me give you some examples of how this works. So let's do magnesium here. Magnesium. If I write out magnesium long form, so let's go magnesium long form, I would have 1s2, then I come down and the 2s2 are filled. And you'll notice this says, this has got 1s, 2s, 3s. So what happens is this becomes known as the S block elements. Before I get into this, I want to write this out. Because any electron that is in this group is going to have a S1 ending. Any element in this column is going to have an S2 ending. Over here, we have P block. P block elements. Because the last electrons are going to have, if it's here, it's going to be 3p, it's going to be P2. So it's either 2p2, 3p2, 4p2, 5p2, 6p2. If it's here, it's going to be 5. So this would be 2p5, 3p5, 4p5, 5p5. These are the D block elements. So we saw here titanium has a 3d2. Now that's not its valence. Its valence is here, so don't get that confused. But it's going to have the last electrons are going to fill a d orbital. And down here, you'll see we've got 4f and 5f. These are the F block elements. So you can add that to your general knowledge of the periodic table: S block, P block, D block, and F block. All right, so let's go back to magnesium. I have 1s2, 2s2, then I'm going to fill 2p6. Because I go 1, 2, 3, 4, 5, 6. And then for magnesium, I'm going to have 3s2. Well, let's look at neon. Let's compare that to neon. So neon is 1s2, and I come over and I do 2s2, and then I go 2p6. Notice that this part of magnesium is equal to neon. They're equal. So I can shortcut magnesium by putting neon in brackets and slipping that up in there. So I can write in Nobel gas notation, magnesium would be neon in brackets, 3s2. And that means the same thing, but it's a lot shorter to write. So what if we were going to Nobel gas shortcut titanium? So titanium is here. If I was filling in titanium, all of this, so the Nobel gas before titanium is argon. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. So this is the same thing as argon. So I can rewrite titanium as argon. Now, actually, technically, the better way to write this is 3d2 4s2, because you want to put your main energy levels in order. But you could also write, I won't count off on a test if you put 4s2, 3d2. So this makes it a little bit easier. Let's do one more. Let's do this guy down here. Let's do, well, let's go over here. Let's do rubidium. Rubidium. So if I was going to write rubidium out long form, see, where do I have enough space? I'm going to have to try to squeeze it in down here. So I'm going to write it out long form. So rubidium is going to be 1s2, 2s2, go to the 2p6. Here I have 3s2. I go to 3p6. Now I go to 4s2. Then I go to 3D and notice I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we know we have 5 d orbitals. Each orbital can hold 2 electrons. And look at that, I've got 10 elements across the d block. So this is going to be 3d10. Then I go to 4p6. And then I go to 5s2. That's a really long electron configuration. Well, luckily for us, the noble gas before rubidium is krypton. So if I come up here, if I was filling in krypton, I would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, which is the same as all of this. So instead of writing all of that out, I can just write krypton in brackets, 5s2. Much faster. So what are our takeaways? We've got 2 takeaways today. Actually 3. First of all, there's a beautiful symmetry, a beautiful elegance to the periodic table. After they placed the elements based on the way they behaved, they found out that it also matched the number of protons it had, and it also matches electron orbitals. The second thing is that we can just look at the table to get our configurations. We can look at the S block, P block, D block arrangement. Keep in mind, it's important to know that this has got to be 3D, even though, so our rows here are period 1, period 2, period 3, period 4, 5, 6, 7. That in the 4th row, we actually start with 3. So that's that fill order exception. And then finally, we can shortcut our shortcuts. So electron configurations are a shortcut for showing where electrons are found. But if we go up to the row before and just put that Nobel gas in brackets, it lets us shortcut our electron configuration. So make sure also you know the difference between orbital diagram notation, electron configuration, and Nobel gas notation. So remember orbital diagram, let's throw that on here for review for our last couple minutes. If I was doing neon in orbital diagram, I would have 1s, 2s, 1s, 2s, 2p, and I would fill this way. So remember fill order, you fill those first, then go single. So this is orbital diagram. On the test, one of the most common mistakes is if I ask for orbital diagram and people give me electron configuration. This is Nobel gas notation, and this is electron configuration. So make sure you know the difference between those 3. Okay, guys, that wraps up the chapter. You've seen everything you need to see. We'll be getting ready for a test coming up. So thanks for watching. Have a great day.